So let's get this party started. Okay, as I mentioned, I'm Bill from TrueTech Tools. We're going to review air velocity testing methods today in the next hour or so. If you're not familiar with TrueTech, we're a stocking distributor of over 50 lines of products, all centered around measuring products for HVAC, energy auditing, physical parameters like that. We do get into industrial parameters and emissions and things like that also. Our goal here is to make measurement science work. We've worked in the industry for years. We try to understand how the products are built. I personally have 3 patents on some products and work for a couple different major manufacturers. So we try to convey that knowledge in addition to sell the products. We do a lot of training, webinars like this one, downloads, guides, videos. There are CEUs offered. In this case, there is 1 BPI CEU, up to 1 offered for this class. We'll go into the details of that, the mechanics of that in just a moment. We do want to see you do it right. We want to see everyone do it right, basically. We offer help to people who don't necessarily are customers. They may have bought something from somewhere else, and we'll just try to help them get up and running and doing things correctly, hoping to earn their loyalty and future business from them. We also have a lot of different ways of connecting, and we'll cover that in just at the very end of the session. So for the BPI CEUs, there's 1 CEU offered for this class. Best thing for you to do is to say on the screen, ask questions. If you have a legitimate question, don't ask a nonsense question, please. If we have polls, in this case, we don't answer the polls, but there's no polls for this session. Big question I always get right afterwards, when do I get my CEUs? The way it happens is TrueTech submits a report to BPI that's automatically generated by the webinar system. And I personally submit those reports within 72 hours, usually within less than 24 hours from the date of the event, from the webinar. After that point, BPI is the one to take care of your record, insert them into your certificate account, your certification account. And at that point, you want to contact BPI after about 3 days, but to give them a little bit of time to do their processing work too. At either this toll-free number here, 877-274-1274, or ceus@bpi.org. Please note, just watching this on a recorded session is not available for CEUs. And it also has to be, it's 1 person per computer terminal, per login, per email address. That's how the CEUs are granted. So it can't be a gang of people watching this on 1 computer screen all expecting to get CEUs. That's just not the way it works by BPI guidelines. If you want to go to our webinars page, these are explained in more detail. And there's also a document there linking back to BPI describing how they handle this. So we're going to break it down into 2 different areas of airflow measurement today. Kind of the way, think of it for residential applications. There's system airflow measurements. That's how much air is flowing through the total system. And the different types of measurement here that we'll cover, and some of them that we won't cover, are temperature rise, the true flow grid, static pressure drop, Pitot tube measurements, hot wire anemometer, and the duct blaster pressure matching method. We also do have Vane Anemometers are also on this list, and we'll cover those too as far as system airflow. On supplies and returns, someone is asking me why the sound is so low. I'm doing nothing in particular on my end. If anyone else has problems, please let me know. It may be something on this particular end user's system that's causing the difficulty. But we're doing nothing in particular to make the sound any lower on our end. Okay, the second of 2 different types of airflow measurements, the way I think of them, are supply and return. Or you could think of supply and exhaust, that kind of thing. Different types of measurement tools that can be used are large vane anemometers, the flow blaster, flow hoods, the flow finder, which is a powered flow hood like the flow blaster, the exhaust fan flow meter, and actually a garbage bag and a stopwatch is a capture device, or large vane anemometer, perhaps, and maybe a mini hood can also be used for supply and return measurements. And again, we're going to break these down and get into them in detail, how they work and how they can be used. First thing I want to get straight is everyone pronouncing the word anemometer correctly. I hear it so many different ways when I travel around and do training at various sessions and conferences. I want to try to make sure everybody pronounces it correctly so we're all using the same language. Let's all try it right now. Even though I can't hear you, I know you're doing it in spirit out there, so give it to me. Anemometer, anemometer. Say it out loud. Okay, there. I think you all got it. All right, so that comes from the Greek word anemos, meaning wind, or this is basically a wind meter, is what we're looking at, an anemometer to measure the airspeed. Something really to think about and to consider is that air, even though you can't see it, it has a mass. Standard air at standard air conditions does have a weight of 0.075 pounds per cubic foot. It does take up space, although it can be compressed. It does take up space and has a specific density. So it does require energy to move this mass of air. And it's really this mass of air that's doing the air conditioning that we're usually thinking about, where we're heating living spaces or working spaces, or cooling them, or humidifying or dehumidifying. We're doing things to the mass of the air. It's that mass that holds the energy, the thermal energy, also the humidity that can also hold the thermal energy in the mass, and then transfer it from the heating and air system to the living or working space. You want to be sure to understand a lot of times we're working in the comfort arena, where we're trying to deliver comfort either for weatherization purposes or for HVAC purposes. But airflow has a huge link with comfort. If there isn't the right of air flowing through the HVAC equipment, it can cause underperformance, which can cause comfort complaints. There's also the correct delivery of air, that conditioned air reaching all the rooms in the living space or the working space. Also not having enough conditioned air to offset the heat gain or heat loss of a room, either due to infiltration, exfiltration of air from the surrounding, or perhaps solar radiation or cooling, or air washing, cooling, things like that. And there can also be too much conditioned air for the heat loss or heat gain. So too much can cause discomfort issues. Too little can cause discomfort issues. Plus, the airflow most equipment is designed for a range of airflow measurement throughout the system. If the system isn't receiving the correct amount of airflow, it can severely affect the equipment longevity, how long it stays in service, breakdown, things like that. I think everyone out there, I'm pretty sure most of you have heard about maintaining your filters. It's a very basic thing. You probably know people that have had that happen to. I do, where a filter blocks up, chokes the airflow on a system, and may cause, say, a furnace to overheat, or an air conditioning coil to ice over because it doesn't have the correct airflow. So these are the kind of things we're talking about, and everything really ties back to the air. So what's a CFM? A lot of times we talk about, this may be too basic for some of you, but just want to make sure we're operating off the same point. What's a CFM? It's a cubic foot or cubic feet of air per minute. So it's a cube of air or a block of air, or think of it as a box of air that's moving through the system, either through the system or in through to the return or the supply. And it's a volume flow rate. So the per minute here indicates the flow rate, or over a certain period of time, and the cubic feet is the volume or box of air that's moving. It's really how much air, the mass of air that's moving per minute. How do we arrive at that level? How do we arrive at what a CFM is? It is usually done with the calculation of the speed of the air over a particular area. So it's kind of clocking the air on the racetrack as it's moving through the system. How fast is it moving? Over what area? Those two multiplied together, velocity times the area, the cross-sectional area, will give you the cubic feet per minute. So when we have these two factors we're combining together, most of the time we're actually measuring is air velocity. We're measuring air velocity with the measuring device, and we're multiplying it by the area, the intercepted area, the cross-sectional area, the area this velocity is moving through. So in many cases you have to take average velocity, because it could vary across the area, in order to get the total CFM, and the open area calculation is critical to getting a correct CFM. So both of these factors, getting both of these right, help improve how correct your airflow measurement is. Someone asked the question, do I subscribe to the 2 square feet of return air per ton? I do not subscribe to most rules of thumb, because you just take it to the rule of just a couple more calculations and understanding the science a little bit better, and you can actually nail the answer. Usually rules of thumb are good over a short range. I would have to take a closer look at that, which I'm not going to do at this point, but the to say that that's going to be an accurate value, because it could vary depending upon whether you're in heating or cooling mode, and also the climate. So if the velocity or the area are wrong, either one, velocity or area, if either one is wrong, it will lead to an incorrect CFM measurement. So it's particularly important too to get the correct area, open area factor, and we'll talk about open area in a minute. Something also to keep in mind is the density of the air, and we talked about air having mass and also being compressible. So if it's compressible, its density or its weight per cubic volume can change how it's compressed, and that change will happen with a change in temperature, change in humidity, and a change in barometric pressure, or alternatively elevation. If there's a density error, if you're using a method that's based upon a specific density of the air, and the density is an error of about 10%, that could cause an airflow calculation error or velocity error of about 5%. So it's important to use the correct measuring technique and using accurate sensors, and considering if you do need to have density correction for the air. Depends upon how close you want to make a measurement, whether or not you use density correction. If the air density is low, usually more CFM are required, or more CFM are required to keep the mass flow rate the same. So if it's the mass of air that's actually absorbing the heat energy or changing temperature in a cooling mode, and you have a lower density air, you're going to need more CFM, or more mass flowing through the system, if the air density is low. So if air density isn't considered in a cooling mode, many systems have low airflow, and that's usually what's found out there in the field. Many systems have too low of an airflow setting. And it could be from that rule of thumb. And I will go back and I will look at that rule of thumb after the session, and come back with some comments on that for the next time I present. So in duct measurements, let's go through them. There's the temperaturized method, which uses the heat flow equation. Again, we're going to kind of break into these in different layers. The Pitot tube is basically a tube in a tube, and we'll show you what that looks like in a little bit. You do need, however, the tool you also need is a pressure meter or manometer to make that measurement. A thermal anemometer or hot wire anemometer operates on the basis of the wind chill effect, and you can very easily demonstrate that self. If you just lick your fingertip and put it out the window in your car in a stiff breeze, you'll feel that chilling. That's evaporative cooling that's happened, and that can actually be calculated if you have designed the anemometer correctly. The Wilson flow grid, or it's in the more common form in the HVAC industry, the true flow grid, that basically uses a Pitot tube array. So it uses a pressure manometer, a Pitot tube array, and it gives you the average all at once, because it has multiple points of sampling across the cross-sectional area. And then there's also looking at the static pressure drop across filters, coils, or heat exchangers, and that's provided there is a CFM chart to do a lookup. There are several groups out there that actually have generic static pressure drops. They may work, but they're really, you're better off if you have a CFM lookup chart, and we'll talk about what that is in a moment. And then there are rotating vane anemometers, which directly measure the airspeed by turning a propeller inside the rotating vane, inside the duct measurement. For supplies and returns, let's break it down again another level. There's the flow blaster, which is a pressure compensated flow hood. There are also, and basically, these are kind of in order of, pretty much in order of cost or complexity. And for the supply and return measurement, coming down from kind of the highest level, the ultimate, the flow blaster, which is a pressure compensated flow hood, or a basic flow hood or capture device, not pressure compensated, but still grabbing the air and channeling it through a funnel. The rotating vane anemometer can also be used at supplies and returns. We'll talk about specifically in a moment how that gets used. An exhaust fan flow meter can also be used within its range of measurement, so you got to be careful about that. And then tougher to do at supplies and returns are Pitot tubes, because a Pitot tube is taking a measurement at a specific point, and again, we'll show you what that looks like with a Pitot tube, the cross-sectional kind of anatomy of a Pitot tube in a moment. But you will have to to measure across, say, this grill here, you'd have to traverse or take several points of measurement on a supply or return to be sure you're capturing all the intricacies and the variations in the airflow measurement. So, and then average all those together appropriately. That can be an awful lot of data and can take an awful lot of time. So it is tougher to do that way. And the same with a thermal or a hot wire anemometer, you would have to traverse and take into account the differences in the flow field. There's different velocities coming out, as you can imagine, behind different parts of this grill or any kind of grill. And when you do supply measurement, you must look at the open area on the supply when you're using any of these, except for the capture devices with the rotating vane or with the Pitot or the thermal anemometer. You must know the open area of this grill in order to do the calculation, because you have to determine what the air velocity is through the open area of the grill. So that can sometimes be one of those limiting points which makes it difficult to take an airflow measurement. So let's take a look at open area on supplies. And I did a little study. I pulled open a manufacturer's data book, supply register, supply grill data book. And I looked across and found that floor diffusers, depending upon their size, have an open area of between 71 and 75% for one design, 66 to 75 for another, 65 to 75 for another. So it seems like we're hovering in that area of around 70 to 75% open area would be a good number to use, at least for this manufacturer's grill. However, if you looked at heavy duty or dual shutter floor grills, it dropped off quite dramatically because there's more hardware that's blocking off that open area inside the grill itself. So that can really throw a monkey wrench into the calculation. And in general, the larger the grill dimension, the smaller the open area factor, because there's got to be more, I believe, because there's got to be more support in there. There's more construction, there's more guts to the grill in order to make it withstand staying structurally rigid. However, if you take a look at this, you can see that there's quite a wide range, and anywhere between 50, looks like 56% on up to 73%, 72.5% open area. But this is the kind of number that you're looking for. The free area, the open area percentage is what you're looking for, because you'll take that and multiply that by your average velocity to get your CFM on a grill. So if you have this kind of data for the grills you're measuring, that's fantastic. That's great. If you don't have that kind of data, that's going to kind of confound your measurements. I'm going to take a pause right here for a drink of water. Hang on. Okay. So the temperature rise method is another way of measuring airflow, determining airflow. It's using the total heat equation, or the sensible heat equation, where you take the CFM of the system, the cubic foot per minute of airflow, can be calculated from the BTU per hour output in heating mode divided by 1.8 times the delta T in Fahrenheit. So you only have to make one temperature measurement here, and that's the change in temperature between the air coming into the heating system and the air exiting the heating system, and divide that, multiply by 1.08 and divide that into the BTUs per hour output. This can be used on natural gas, oil, propane, electric furnaces, but you do have to be careful about variations in fuel quality from if you're trying to use the nameplate data for the BTU output. That may cause, if the fuel is richer in heat or thermal content or energy content, it could change this a little bit. Also, the heat from motors that are using to propel the distribution fan, moving air through the system, can also affect this, and it really isn't counted inside this calculation up here. For the fuel oil type, or gas oil and propane type. For electric furnaces, it's a little bit easier because you can actually just change kilowatts into BTUs per hour output and then do that calculation correctly. Still paying attention, though, to the motor heat. And you do also have to wait for the appliance to reach a steady state efficiency level which may take up to 10 minutes or so, or just checking to see that you've achieved that stable stack temperature in order to get this type of measurement. And for combustion systems, to get the BTU per hour output, you can look at the BTU hour input times the steady state efficiency for a combustion system. And that is not the AFUE. That's not the yellow sticker data. That's the government standard test. You actually have to use a combustion analyzer to determine what the current steady state efficiency is of the system. So as you can see, that this does get a little bit complex. If you really want to follow the letter of the law and do it correctly, you do have to be careful about motor heat, variations in fuel quality, and you also need a combustion analyzer to get that BTU input. Sort of a lot of work in order to get back around to the airflow measurement. And when you do this, the technique, of course, matters. In this case, you want to measure the temperature rise of just the air that's moving across the heat exchanger, because that's what's being heated up, and that's what you're looking for in this equation. You want to make sure you're out of line of sight of the heat exchanger, because you're going to get a radiant effect on your temperature measuring device. And if there's a bypass humidifier, that should be closed if it's present, because that could cause air not to be heated, or to alternately to cool and to throw off your measurement. So again, this can be quite a complex measurement when you really get down to doing it correctly. So let's take a look at hot wire, or a hot bead type anemometer, or a thermal anemometer. And again, we mentioned it works by the basis of the wind chill effect. So a bead is actually heated up on the tip of the probe, and this bead with a temperature sensor beneath it, the circuitry in the unit inside the thermal anemometer actually measures the radiant heat coming off of this bead. And as the air velocity picks up and it pulls heat away due to wind chill, the circuitry in the unit raises the temperature of the hot wire, like a toaster wire, until this temperature sensor in here actually says you're back at a stable temperature. The amount of current that's required to keep that bead hot enough, to keep the temperature warm enough in that area, is what is measured. So this is a current measuring device, measures the temperature of measures the current flow in order to keep a standard steady temperature of the hot wire inside the heated bead. What's great about this type of technology is very easy to use. You just power it up and it gives you the number. It has a fairly broad range of measurement. It doesn't take much air velocity to begin the cooling effect, and it operates over a broad range. There are limitations, however, to doing this. Denser air has more mass, so it would carry away more heat at a given velocity. So if you don't correct for the air density, that could cause a variation in your reading. It's also subject to contamination. If you got something, some grease or other, or fuzz or any kind of lint across that wire, it would act like a jacket, and it wouldn't allow it to take away as much heat. So that would give you a false reading of the airflow's potential to take away heat. So you wouldn't want to use this, say, in a kitchen exhaust. It's also intercepts a fairly small area, and we'll show that in just a second here. Yeah. So this is the tip of a pen. That is the hot wire bead. That's where the measurement's taking place. So basically in this small area at this tip, that's where the measurement's taking place. And that's the air velocity that's being measured. If the air velocity is a high variation and it's 10% different here and 20% different here, you can just imagine how many different measurements you'd have to take to get an accurate reading. So it has a very small intercept area. That's one of the limitations of it. And it's best used in duct measurements, where airflow is stable, it's laminar, you've developed flow fields, versus at supplies and returns, where there tends to be a lot of turbulence, because the purpose of a supply grill especially is to throw air into the room to cause mixing to do the conditioning. So as it's throwing the air, it's redirecting, diverting it, deflecting it, and causing it to have a variation in its velocity profile, which then makes it harder to measure at a supply. Good hot wire anemometers range in price from $250 to over $600, but there are some really good ones out there for $250. And we talked about the density effect. Because they are based upon the thermal measurement principle, it does autocorrect for, most of them do autocorrect for the temperature of the air, or the density of the air based upon temperature, but they aren't correcting for humidity or barometric pressure. They are not correcting. So let's take a look at another method, and this would be the pitot tube or the pitostatic tube. Here's basically a pitot tube. So we talked about it being a tube within a tube. There's an outer section, an outer channel, which picks up the pressure or the balloon pressure of the duct. Imagine this being placed inside a duct. Picks up the balloon pressure of the duct only, and then the tip of the pitot tube has a hole in it leading straight down. That tube picks up the total pressure. The total pressure is actually the sum of what's called the velocity pressure plus the static pressure. So by subtracting the static pressure from the total pressure, and you do that inside your differential manometer, you are left with the velocity pressure. So this air pressure pushes or pulls on a sensor, the membrane inside a sensor, a pressure membrane, and the difference between total and static gives you velocity pressure. It's pretty easy to use. You have the pitot tube. It can range anywhere from $50 up to a couple $100. The tube itself, you do need a manometer, a pressure meter. It's pretty cost effective. A combination with a magnehelic and a static pressure tip, you can be well under $200 and be up and running doing the pitot tube measurement. The limitations, again, are denser air has more mass, and we talked about that. Here it has, denser air would have more pressure at a given velocity. So imagine having a marshmallow thrown at you versus a tennis ball. You would feel a different type of pressure when that hits you. So lighter air, the marshmallow, would have less impact pressure than denser air or the tennis ball. So that gives a variation that could affect the pressure reading. Also, lower velocity limits are harder to achieve because that means a lower and lower and lower pressure. So you will need a precise manometer in order to do the calculation to get that low pressure reading. And these, again, are best used in duct measurement. Again, we talked about it's actually got a fairly small intercept area, and also its ability to do kind of a scan across the velocity field at a supply or return. And we talked about the price range in the $200 range for a combination of a pitot tube plus a manometer. So for doing any kind of, or basically the pitot tube, hot wire, or mini vane in duct measurements, you want to look for a straight section of duct about 2 to 3 duct diameters or duct dimensions away from turns and fittings. So this was a picture taken in a lab, and so at this point here in this return drop, we're a couple 3 duct diameters away from this transition in this bottom return, and from any transition where the supply is coming in. So it's best to take in the return where you have a pretty steady, stable airflow. Taking these kind of measurements in the supply, there can be a lot of different things like air cleaners and air conditioning coils and heat exchangers causing variations and ripples in the airflow, where the return has had a chance to develop a nice, even, uniform flow field, velocity field, in order to take a good measurement. And we show 3 points here. We do have some downloads and guides on the TruTech site for the number of points you'd want to take a measurement going across when you're doing an in-duct measurement. We have that available in our free download section. You do that if you're taking multi-point measurements, but some of the devices actually have the ability to scan and do a linear average. That means it's always taking an average as you move it across the duct, which is a lot easier than stopping at different measurement points going across the duct. So there's a couple different ways, either point measurements or moving averages, line averages, can be used to make in-duct measurements. The true flow plate, or the pitot array, or flow grid as they're sometimes called, basically that's what it is. It's like multiple pitot tubes that are operating over a specific area in this plate, and they're sampling all at once all the velocities. You can see up here the cross section, there's a cutout, there's a circle. This tube itself will have a total pressure port, and it will also have the tube behind it will have a static pressure port. So it's collecting static pressure information, collecting total pressure information, and then when you hook the hoses up to your manometer, it can do a calculation and give you the velocity pressure, and then do the calculation with velocity pressure to give you the total airflow over this system. The true flow plate is manufactured by the Energy Conservatory. Comes in a couple different sizes. It comes basically in a kit. that can be used across a wide range of residential heating systems. It's pretty fast to set up. It's very adjustable. You just snap on edge pieces in order to make a snug fit in the filter slot, or in a central return if you don't have a filter slot. The limitations, however, the same as the pitot tube, and that would be the main limitation will be the density correction. However, the meters do have the ability to do some of the density correction factors to give you an improved reading. Because this is put in place of, many times in place of, a filter in a filter slot in a residential system to get the total overall velocity, it does present it may present a slightly different pressure drop than the filter would. However, there is a correction factor called the normal system operating pressure, which will allow it to move very close to runtime conditions. Even though it's not the original filter, you can take a differential measurement and use it. The Energy Conservatory does a great job in their instruction manual. In fact, you can download it for free. I think we have it on our site, but I'll make sure that we have it up there because it gives you a very good overview of the technology and how it works and the correction factors. You do need a digital manometer to use this, and I would say you need a precision manometer and one that has the calculation for the flow grid in it. Both the Retrotech and the Energy Conservatory manometers have those calculations built in for true flow grid measurements. And its main application is system airflow. It's not meant for supplies or returns. And the cost for the unit itself is around $800 plus your digital manometer, so it gets in the $1,700 to $2,000 range for your combination. But you may already have a precision manometer if you're doing duct leakage testing or blower door testing, so this would just be an add-on of about $800 to be able to do total system measurement. There's another method that involves using your duct blaster or duct leakage tester. It's a pressure matching method. So basically you look at the pressure, the normal system operating pressure, and match it with the duct blaster, which is retrofit over the fan compartment, the blower compartment, to match that same kind of pressure running through the system. But because the duct blaster or duct leakage tester is a calibrated fan, it can actually measure the airflow through it. So you run the system normally, you take a static pressure, or you take a pressure measurement of your system, then you take the cover off and you match that pressure with the duct leakage tester, and then measure the airflow rate through the duct leakage tester. It's got the benefit of having the accuracy of a duct blaster or duct leakage tester. It may already be a tool that you have, but the limitations are fitting the device to the air handler cabinet every time. You have to make sure you have a tight seal every time, and basically it's a mock-up that you have to create every time, and there would be a multi-step process to follow. Again, that's in the actually the duct blaster operating manual has the instructions on how to perform that kind of test, but there are several steps to it, and you have to do them all in correct order to record the correct information. And again, this is also just for total system airflow. It's not meant for supplies or returns. And the cost there would be about $2,000, the cost of a duct blaster or duct leakage tester. So let's now look at a static pressure tip. That's something you're probably familiar with. You've heard about taking external static pressure measurements. How does that work? What is that device? What's it made of? Well, I look at a static pressure tip and I think of it as half of a pitot tube. Basically, the center section is sealed off, and all you have is one tube, and you just have the balloon pressure or the inflation pressure of the duct pressing on perpendicularly to the tube itself. So the static pressure tip is aimed into the airflow, and the static pressure is just the balloon pressure which is around, surrounding and inflating the duct. Sometimes you can hear ducts inflating in larger systems going boom, 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 boom as the system turns on. If you hear a large air handler turn on, that kind of pressure that's inflating the duct is the static pressure. So this total pressure moving into it is not actually sensed by the static pressure tip. It's, again, pretty easy to use. You just stick the static pressure tip and head it into the wind, point it into the airflow. It's cost effective, but it also does not account for density considerations. So if you have higher density air, it's going to have a little bit different pressure, and you gotta take that into account. And the static pressure does not directly equate to airflow. You have to use it in reference to a manufacturer's CFM chart. And again, this is mainly for in-duct measurement, and it's for total system measurement. Again, this isn't for supplies or returns. The price for a static pressure tip is usually under $20. You need 2 of them because you need to take a difference in static pressure over a device. So let's take a look at using this static pressure tip. Here's the tip itself, but then it has to be used in a certain way. It's used in order to measure total external static pressure. So the manufacturer of the heating or air conditioning equipment would profile their heat exchanger or their evaporator coil or their system together and take a series of readings of cubic feet per minute or airflow and pressure drop. So they would make up a chart of this information and then provide that chart to you in the form of a table of CFM at external static pressure for different configurations, different types of their equipment, because there are different models and different elements are considered in each model. And just for a ballpark to kind of set the frame, the industry standard for total external static pressure is usually around 1/2 inch of water column and ranges from 0.3 to 1 full inch of water column are possible and are out there. When you take into account ECM or electronically commutated motors, this makes it a new ballgame, and we'll talk about what that difference is a couple slides from now. So let's take a look at a particular manufacturer's CFM lookup chart. This is the chart that we're referring to. This is the key to translating your static pressure drop to actual airflow measurement. So this is airflow pressure drop table, or for this particular wet cooling coil. Now here's an interesting thing. How wet is wet, or is a dirty wet coil different pressure drop than a clean wet coil? I'm thinking the manufacturer probably tested a clean coil in laboratory conditions, and you may be encountering a wet coil that's got lint or fuzz or improperly filtered air coating it, which is going to change the pressure across it. So again, this does come with some cautions. You have to know what you're measuring. And this is the coil only airflow rating. So it's not for the heat exchanger, the motor compartment. It's just over the air conditioning coil. 2 things that you're going to get out of this are the inches of water column and the CFM. Where you see this information, the inches of water column is shown up here in the top, and the CFM is shown across the table here. You also have kilopascals. They're made these tables for international purposes, so you have kilopascals and liters per second. The kilopascals will be the second number in brackets here, and the liters per second, that's the airflow in metric, basically. So let's take a look at a specific model. Again, we talked about this varying for different types of systems. We have a 3624 coil, probably 3-ton system. That's the coil model number. And if we're just looking at that one, you can ignore the rest of the chart. It kind of makes everything gets a little bit simpler all of a sudden when you're just looking across one line. And let's say we have measured our total external static pressure over the coil only, again, coil only, of 0.14 inches of water column. That equates to around 1100 CFM of airflow through that coil. So that's how these systems work. We did talk about the difference in modern systems tend to have ECM motors for energy savings purposes. The traditional type of blower motors are permanent split capacitor, and those have an impact of decreasing airflow as static pressure increases. Think of it kind of like your heart pump. Your heart pumping against higher and higher static pressures are inside your body. They would actually get less flow as the blood pressure increases. The newer type of motors, which are used in a lot of higher efficiency systems in order to gain the maximum in energy efficiency, are electronically commutated, or ECM motors. They actually auto adjust the RPM, or the speed, the revolutions per minute, of the blower motor and the power to keep the programmed airflow. So they know they need to turn so fast in order to move the air, and they adjust and continue to keep the air. moving at a programmed flow rate to get the programmed CFM. So the airflow actually varies very little as the static pressure changes, and the motor actually can sense, I believe it's usually through the torque that's going through the motor, can sense the resistance to the airflow, and it knows it has to pick up speed in order to achieve the specific CFM. They sometimes have programmed speed limits, so they don't run out and destroy themselves and self-destruct. But if the resistance grows and gets higher for the system, it will try to keep up at the sacrifice of power consumption. Usually these are installed to save energy, but if you're not careful and it's has a situation where the static pressure is increasing, the power consumption may be very high and actually more than a PSC motor. Static pressure measurements on an ECM system will pretty much check the efficiency and tell you if they're within the design parameter, but there's very little change in the CFM with static pressure, and I'll show you that in a chart in a minute. So it's really not, static pressure measurements on an ECM motor system are really not necessary, not advisable, and don't give you a heck of a lot of resolution of data. You really just need to know what that motor is set at, what it's trying to achieve in terms of CFM, and then look at static pressure. If it's too high, that may be affecting the power consumption of the motor. So let's take a look at a different chart here, and this happens to be for, and again, everything varies depending upon the equipment size and the equipment type. So this is a -21 model cabinet with no electric heaters installed because they can increase the resistance to airflow. And we'll look in this case at a 1/2 inch of water column, 0.50 inches of water column drop for the external static pressure, and see that in this case the chart shows you 3 numbers. The top one is 986, and that's the CFM. The middle one is the watts of energy being consumed, or 189, and the bottom one is the RPM, 741 RPM coming through the system. So this is basically what this type of ECM chart does. I've got a question here. How does the ECM measure static pressure in order to keep up or slow down? It doesn't measure static pressure. It measures torque. There's an internal sensor on the shaft of the motor which actually measures the torque and can tell how much energy is being consumed in order to keep up, to keep the speed of the shaft going and keep on throwing the same amount of air through the system. So it's not actually measuring pressure. So here's the CFM again, the watts, and the RPM. Now let's take a look at the external static pressure changing from 1/10 of an inch of water column all the way up to 0.9 inches of water column, and just observe these numbers: 993 CFM, 990, 988, 987, 986, etc. Very little change all the way across. A change of 7 CFM across a range of pretty much 100% of the range of the external static pressure. So basically it flatlines. But let's go back to that one example there and remove these circles and take a look at the power consumption, the watts. 117 all the way up to 272. That's well over double the power consumption for actually a reduction in the amount of airflow. So that's where you have to be careful with an ECM. If it's undergoing too high static pressure outside of its range, it could be consuming gobs and gobs of excess electrical energy. Let's move through that and take a look at another chart. Here we're looking at the 04-M model on this grill. On this system. So again, just block out the rest of the chart. And we'll take a look at 1/2 inch of water column is the external static pressure that's measured. And again, here's kilopascals are given. And we're looking at the blower speed setting of medium-low. And it should be running at about 775 CFM. At 0.6, you'll see it actually drops off to 730. And at 0.1, you see it's as high as 920. So at this point, knowing what you know, you'd be able to say this system uses a PSC motor, because this motor responds to the amount of static pressure that's in the system. It operates at a very low static pressure, very high at the medium-low setting for delivery of air, and at higher static pressure, lower, even like around 25% lower delivery of airflow. So that really underscores how important medium-low has quite a broad definition, from 920 to 730, depending upon the static pressure of the system, which is related to the way the ducts are designed, the way they're installed, the filter that are in place. So that all has a big impact on the system. So to measure the static pressure drop, and again, we focus on it a lot because it is one of the most common measurements out there, you need to have the manufacturer table of pressure profiles. So we just covered a couple different types. And it's usually the air conditioner or the heat exchanger, or they'll tell you what type of element you're measuring over. And you have your two static pressure tips located pointing into the wind, into the airflow, measuring just the balloon or static pressure hooked up to your digital manometer. Again, this combination of the manometer and the static pressure tips is pretty low cost, pretty easy to use. You just need a digital manometer to use it with. You don't need a precision manometer, just one that does measure down to 1/100th of an inch a Waller column. However, the limitations are you have to have the manufacturer's equipment table really to be able to say you have a CFM reading. The known resistance can change if it's a wet coil or dirty coil. We saw that on a couple of charts. They say specifically it must be a wet coil, and probably a clean wet coil. You have to be careful to make sure that you're actually not picking up any kind of velocity drag or turbulence near the edge of a wall, that your pitot tube is really sticking into the airstream and sensing that total static pressure. Caution again about air density correction, and careful about drilling into things. You don't want to puncture an air conditioning coil or a heat exchanger when you're doing this kind of test. So the applications again are for in-duct measurement, for system airflow measurement, and the price range is around $200 to $300 depending upon the kind of manometer that you choose. What you've probably seen so far is we go across the array of different measuring types. The easier it is to do a test, the less limitations or factors you have to worry about, the more you pay for the equipment. The more limitations or factors you have to concern yourself with, usually the less expensive equipment. So it's a kind of combination we call pay for performance. Either there's a lot of human intervention involved and a lot of thought, or you can just let the equipment take over and do it. But you're going to pay more for that equipment than you would for equipment that requires more people skills to make it work. One of the rules of thumb that I like to give is that you should avoid the use of standardized tables or charts because they usually do not provide even a reasonable estimation of airflow. I've heard of a group that I really know and trust lately talking about their standardized tables, and I'd like to study them a little closer. Maybe they've kind of cracked the nut on this, the Rosetta Stone here, but I'm still skeptical. Because coil designs vary in the number of rows, the fin spacing, the open area, the manufacturer accounts for all that as they do with the model numbers when you look at their charts. So that's why it makes it very difficult to use a standardized table or chart. If you take a look at this picture, you're probably wondering exactly what it is. And it's actually a picture of my air conditioning coil in a system that I replaced in my house just over a year ago. I took this with a visual inspection scope. It's really hard to believe there was any airflow moving through there at all. There was no filter present. Thought I had a filter that was working that obviously wasn't working. And there was a lot of collection of debris, lint, and fibers on the air conditioning coil. This caused, it was a PSC motor, this caused a fairly high pressure reading, and you could look at the manufacturer's chart and say, well, high pressure reading, you're getting a lot of airflow or a little bit of airflow, and it may not necessarily be true. It could be due to contamination and not necessarily to the system itself. So you do have to be careful and, again, knowledgeable of what's happening when you do take these external static pressure tests. That's a picture of the coil as it came out of the system when we did do the replacement of the system. If you're interested in delving into this a little bit more completely, again, this is one of those things which a lot of people are using. We do have a 20-minute video lesson, which you can get to from our resource page, or you could type in this bit.ly link, bit.ly/esp-video. That's all uppercase. Make sure you hit all uppercase for that. And we also have a free download on total external static pressure testing. That's bit.ly/ttt-esp. Those are all, again, all uppercase. So those resources are available to you if you want to see to get a little bit more in depth about this. Okay, let's move to Vane Anemometers, which can be used the large vane at supplies and returns and the mini vane or the small vane inside duct system or for total system measurement. So basically you have a propeller which rotates proportional to the speed of the air. So it's like a wind vane. And that either uses, in this case, uses an optical pickup. So there's actually no friction. There's just a little bit of friction from the bearing, but there's an optical pickup that counts how many times this revolves. And in the case of the mini vane, it uses an inductive pickup. Got a question here. Okay, I think the person answered their own question. Great. The Vane anemometers do not require density correction because they're actually measuring airspeed directly. They're one of the few measurement devices out there that actually measure the speed of the air directly. And they also take into account, when we're talking about those pitot tube arrays or thermal anemometers, having to look over an area, these devices, the Vane anemometers, are actually averaging over an area, and either over a large area across this 4-inch circle, or a larger in relation to a pitot tube or a hot wire anemometer, and across this 1/2 inch diameter circle. So I call this a large small area. They're also minimally invasive. The profiles are designed not to interfere with the airflow or provide any kind of back pressure or blockage. However, it does take a little bit of oomph to get the vanes turning on the anemometer. So that means that they're not very good for low airflow readings. They don't operate well when there's turbulence or backflow. If you have air that's actually swirling coming off of a fan, it will actually induce the propeller on the Vane anemometer to swirl, and that swirl is not representative of the velocity measurement. It's representative of the swirl, so that can cause a problem too. So you have to look for some fairly stable and uniform air velocity flows away from the fans. Having the probe at the incorrect angle during a test doesn't usually cause too much of an error. In fact, 10% off angle, it produces only about a 1% error variation in the tests that we've run on it. And also you have to be aware of the friction of the propeller bearings and the amount of propeller bypass. And what I mean by propeller bearings are those devices that hold that shaft in place, make sure that they operate pretty freely. And propeller bypass, you have to look to see if there's actually air that can slip by through this cross-sectional area by the blades. In the case of this design, the Tester 417, the blades are actually one piece molded to an outer wheel or hub, which keeps their position pretty much perfect during the whole lifetime of the product. So these are the kind of little factors or features you look for to get the better quality measurements. Large vane applications for large vane anemometer supplies and returns, of course, for the large vane, especially in flex duct systems where it's hard to get a total system measurement. You may need to measure just the return in order to be able to see how much is flowing through the system. And mini vanes are used for in-duct measurements on hard duct systems. Using a mini vane in a flex duct system or even a pitot tube or static pressure, it's very difficult because there's so much turbulence due to the corrugation inside the flex. And the price range of these kind of devices between $500 and $700 for the mini vane or large vane. Here's another little rule of thumb that I have, Rule 724, and this is using scoops, mini hoods, or funnels with rotating vane anemometers. Basically, they are designed for very low flow applications. Anything above about 75 CFM, there's a huge back pressure effect wherein you're restricting the airflow from this mini hood. I'm not talking about flow hoods, I'm talking about mini hoods, the kind that are about, say, a foot to 14 inches in depth. This causes back pressure in the system and are not designed to be used in any kind of measurement above 75 CFM. But they can be used in low flow measurement situations. The thing to think of here is how much airflow can you get if you are covering, if your measurement device is actually covering the grill. You can still be pushing on it, but you're not going to get very much airflow in or out of that supplier return grill if you have a restriction placed over it. However, with the exhaust fan flow meter, this is a device that's actually designed to be used to measure exhaust fan flow, but it's not designed to be used for supply and return flow. It's for exhaust fan flow anyway, hence the name. You do need a precision digital manometer, that is something with a Pascal readout. It does have a measuring range of from 10 to 124 CFM, so it covers that nicely, that low range that's typical of most types of exhaust fans or ventilation fans. The actual device you can use, the pressure measuring device, it can read out directly using the mode on the DG700 or the DM32 by Retrotech will actually give you the direct readings in CFM. Just make sure you enter the right mode and you have entered the right shutter position, because it's basically, this does create a pressure on the system. It's measuring the pressure, the static pressure inside this box and channeling the airflow through a specific slot. So I believe it's either A, B, or C slots. You would set that up corresponding to the mode on the pressure meter, and then would give you directly the CFM. Or alternatively, there's a sticker or a chart inside the instruction manual or a sticker on the outside of the exhaust fan flow meter. So all you need is a Pascal type resolution meter, hook it up, and then look at the chart inside the box itself. It does need to be placed over a fan grill, and the air is drawn through the calibrated opening. And again, it's for exhaust fan flow only, which means the air is drawn through here, air pushing out through here. You can get a pressure reading from it, but it's not really designed to make that into what's called a measurement. You do want to make sure that the opening is adjusted to minimize the back pressure while trying to capture the maximum accuracy. So there's a little bit of give and take with this, but the device is itself about $135, but you do need a precision digital manometer. One without any calculation can be had for around $500, and then on up to $800 to $1,200 if you want one with the calculation, or you may already have one with your blower door or duct leakage tester. Okay, let's move to the capture devices. Plastic bag and stopwatch. Sure, pretty cheap. Accuracy, questionable. There's a lot of human element involved there, but you can get some pretty accurate numbers if you do hit some prescribed procedures correctly. Repeatable, you'd have to have that. Again, that human element has to be very repeatable with it. Flow hoods are used a lot in commercial and residential applications. And they capture the air across a specific area, channel it through a known area, and then have a pitot array, most usually, or sometimes a hot wire anemometer is used actually to measure across this known cross-sectional area. And the air comes through, it's turned into a laminar flow. Some of the devices have little grates that go inside to make the airflow more laminar, to make it more uniform, and to improve the reading. These devices are pretty fast to set up, pretty easy to use. They are a little bit bulky, a little bit heavy, a little bit costly, but it does capture all the air. In this case, you don't have to worry about an open area factor. You're basically just capturing and measuring all the air if the hood skirt is right. You can take snapshots of the reading, and many times the meters on the flow hoods have multi-functions. You can plug in different probes or use it as an auxiliary pressure meter. So there's other benefits you get out of the device. There are typically two ranges to it, up to 500 CFM and up to 2500 CFM are the two ranges. So you sort of have to know what your target measurement is, what you're going to be measuring if you're going to use, say, what they call low flow bolometer or one of the standard capture flow hoods. The limitation here is the accuracy is somewhat mass dependent, but it can be corrected inside the manometer. Some of the manometers are smart enough where you can input the current barometric pressure, the temperature and humidity of the air, and it will do all those density corrections and give you a perfected reading of the airflow moving through it. And there's also the impact of back pressure. Even though it is a very long throw in the skirt, it can still cause back pressure at high enough flow values. There are back pressure compensation flaps that you can introduce, follow the manufacturer's directions in order to make the device have a better operation when it does introduce back pressure. And the cost here, the $10 is for the garbage bag and stopwatch. $1,500 is the range for the low flow bolometer, and 3200, 28 to 3200 for the 2500 CFM bolometer or capture hood. So, and we sell all these devices, everything we talked about up to now, we sell at TruTech, basically everything in this presentation. So let's talk a little bit about this plastic bag measuring device, how to measure airflow using a plastic bag. This slide is courtesy of Bruce Manclark, who's from Oregon, and Bruce is a good friend of mine for many years. This is Bruce right here, and at the latest presentation, we coined a name for this very sophisticated process, the polymeric volumetric capture device. We figured it needed a very royal name in order to be considered amongst the elite of airflow testing devices, or it's also known as the garbage bag. Again, the basic principle of operation, it works by timing how long it takes to fill a known volume with air. The things you have to be careful about is the definition of fill, the ability to take the timing, and also not to restrict the airflow. Again, like we talked about the smothering effect, if this introduces a back pressure, then you're no longer measuring the airflow out of the grill, you're just measuring a reaction to the back pressure. One of the things Bruce taught me was he uses a pressure spike inside the bag to indicate when it's full. He actually cuts a hole in the bag, tapes a hose or a Pitot tube, or excuse me, a static pressure tip into it, and then reads the pressure in it. And as the pressure, as soon as it spikes, that indicates the bag's full. That means it's begun to back pressure the system, and then you know the bag is totally full with air, and it's not over pressurizing the air, but it's just full. Here's the garbage bag formula. I'll leave that on the screen for a second, but basically you have to have the bag size in gallons, correct from cubic feet to gallons, and correct from seconds to minutes to get CFM, and divide this all by the seconds to fill the bag. So for this example, if you have a 55-gallon bag, you do the correction factor to get it to cubic feet, you do the factor to correct from seconds to minutes to get the CFM, and it took, for example, 4 minutes to fill. So that would be, the math works out to 129 CFM. So that's your polymeric volumetric capture method. And here's just a quick chart taking that seconds to fill with a 55-gallon bag and a 33-gallon bag. So you can see the range and kind of the resolution of airflow. You have to be pretty darn quick to measure something in the say 200 plus in order to be able to hit these half-second marks and to know exactly when it hit the pressure full indication. Got a question here. Is there greater accuracy using smaller bags? I would say no, because those smaller bags are going to fill more quickly, and a quicker filling bag is going to be more dependent upon the starting of the filling process and then the stopping when the pressure spikes and is full. So I would say smaller bags are probably going to be a little bit less accurate. So let's move to another capture device, and that would be the flow blaster, which was introduced a couple years ago by the Energy Conservatory, the blower door, Minneapolis blower door and duct blaster folks. This is actually an accessory that's added on to a duct blaster. What it does is has a grill skirt which picks up and directs the air in through a measurement array, and then uses the digital manometer that comes with the duct blaster and the fan controller to do some auto compensation and to run the speed of the duct blaster, this compensating fan, to run it up and down until it achieves neutral pressure between what's under the skirt and what's in the room. So this allows it to capture the airflow but not affect the pressure. If it starts to smother the airflow and back pressure the system, pressure will increase under the skirt, the fan will turn on and will run up until that pressure is neutralized and makes the skirt invisible, makes the whole device pressure invisible to the duct system, so it maintains the flow. You need a battery pack to wear actually on your belt when you run this to power the duct blaster, and it does provide very precise measurements. I've heard sub 10, within plus or minus 10 CFM or even closer than that to actual measurement. It does test out well. The device itself, the attachment is around $1,100, and you need to attach that to just a duct blaster. That's the only device it attaches to. So you either need to get one or to have one, and they're around $2,000. So the total cost is around $3,000, $3,200 in order to do this this flow blaster auto compensated type measurement. There's there's a new kit in town called the ASIN Flow Finder. The Flow Finder Mark II is actually distributed in North America by Retrotech and also sold through TrueTech. This device actually has an internal fan and a sensor to compensate for back pressure, similar to what we saw in the flow blaster just a moment ago, but this is an integrated device. This is all this does. It's not a duct blaster. It's a lightweight device that can be used to measure up to 500 CFM, supplier return airflow. It can actually data log on this color screen, the color touch screen here. It gives really the ultimate accuracy. I would say the same or perhaps a little bit better than the flow blaster. I haven't seen the two of them compared, but they're really up there neck and neck in terms of precision and accuracy. It's a one single piece construction. There's no assembly, no tools required. You just basically turn it on and make a measurement. It's lightweight. It weighs in at about 5 pounds. So it's an easy device to carry around and to use. And again, you pay for this performance, all this precision, this ability to get the kind of measurement that you want quickly, easily, data log it, see it on the screen. You pay for that performance. Very little human intervention, very little impact from back pressure. So that's around $4,000 for that device. So right now I just wanted to stop for a moment and see if there's any lingering questions that I have not answered. And just have a little bit of fun looking at our question panel here. Okay. All right, so wrapping it up, just want to make sure everybody's aware of our resource page. It's a new page we've developed at TrueTech. It's the very first category because we get tapped for a lot of resources and a lot of questions. It features our downloads, our featured downloads, and you can get to more downloads by clicking here, our latest videos, and then also the software, technical training downloads, all by different topic area here. And you get it at truetechtools.com/resources. I got a question here about calibration of equipment. Calibration is either required by your certifying body, say ResNet, and they will specify when things need to be calibrated, but most usually it's addressed by the manufacturer. Some of the devices I talked about, there is no calibration possible. They can be checked against a reference standard. So for example, some of the smaller manometers, the less expensive ones, you would have to check them against a kind of a gold standard device. Even your digital manometer that you use with your blower door or duct leakage tester, duct blaster, those are sometimes done. You do a cross check against another one to see if it has a comparable reading to like a gold standard device. Flow hoods, all the manufacturers do offer calibration of those. We can facilitate with that. And I'm familiar with Testo's calibration. They have a fairly extensive airflow calibration test lab. They will do calibration of airflow. They have a top-notch NIST quality airflow test lab, a wind tunnel to do testing there. So that's available. We don't do airflow testing at TrueTech. We do calibration of combustion analyzers, but not of airflow. Okay, I don't see any other questions. All right, I'm going to stop the recording here.